141b. K2-141b is a rocky lava world located about 200 light-years away. It orbits so close to its star that a year lasts less than 7 hours. The day side is a vast ocean of magma, while the night side is frozen solid. What makes this planet unique is its weather cycle. Instead of water, rocks circulate between the surface and the atmosphere. On the hot side, rocks and minerals vaporize into gas. Winds carry these materials to the cold side, where they condense and rain down as solid rock. These rocks then flow back into the magma oceans and restart the process. Anyone standing here would face a constant bombardment of rock rain, a deadly storm of stone moving at supersonic speeds. HD-1897333b. HD-1897333b looks similar to Earth from a distance, with a blue color that suggests oceans. But up close, this resemblance is deadly misleading. Winds here blow at 7 times the speed of sound, more than 8,000 kilometers per hour. Any visitor would be swept into the atmosphere and whipped around the planet endlessly. Adding to the horror, the blue color does not come from oceans, but from silicate particles in the atmosphere. These create rain made of glass. Shards of glass, driven by supersonic winds, would slice through anything exposed. Survival here is not possible, as both the atmosphere and the weather are lethal. HR 5183b. HR 5183b is a giant planet about 3 times the mass of Jupiter. Its orbit is highly elliptical, taking 74 years to complete a single loop around its star. When the planet moves far from its star, it drifts slowly, but as it swings close, gravity accelerates it dramatically. This sudden change of speed earned it the name Whiplash Planet. The intense gravitational forces disrupt other planets in its system, acting like a cosmic wrecking ball. Any human visitor would be crushed by the massive gravity, while the constant shifts in orbital velocity would destabilize any spacecraft trying to remain in orbit. Living here would mean enduring constant gravitational stresses, far beyond human tolerance. WASP 107b. WASP 107b is sometimes called the Marshmallow planet because of its extremely low density. It has no solid surface, meaning there is nothing to stand on. The atmosphere is heated to about 1,000 degrees Celsius, turning sand into silicate vapor. This vapor rises, cools, and condenses into tiny grains of sand, which then rain down at high velocity. The process repeats endlessly, creating a storm of falling sand. Any object in the atmosphere would be shredded by these sharp grains, while floating in a superheated, unstable environment. Unlike Earth's sandy beaches, Washington SP 107b is a desert of fire and storm, with no ground and no safe refuge. HD 1897333b. This planet is a hot Jupiter orbiting a K-type star about 64 light-years away. It was discovered in 2005 through transit and radial velocity methods. The planet orbits extremely close to its star, at only 0.031 astronomical units, completing a full orbit in just over 2 days. Its mass is about 1.13 times that of Jupiter, and its radius is 1.14 Jupiter radii. The density is close to 0.94 grams per cubic centimeter, indicating a gas giant structure. Its most striking feature is its cobalt blue appearance, which is not due to oceans but to high-altitude silicate haze scattering blue light. The atmosphere is violent, with dayside temperatures of about 1,700 degrees Fahrenheit and winds up to 5,400 miles per hour. These winds drive molten glass rain sideways across the planet. The atmosphere is evaporating at a rate of about 100 million to 1 billion kilograms per second because of intense stellar radiation. It is tidally locked, meaning one side always faces its star, while the other remains in perpetual night. The planet has no solid surface, no moons, and no rings. Any potential moon would be stripped away by tidal forces. It is a benchmark planet for atmospheric studies since it was one of the first exoplanets observed with transmission spectroscopy. Observations from Hubble, Spitzer, Chandra, and more recently JWST have revealed sodium, water vapor traces, heat distribution, and atmospheric escape. This world is not habitable, but it remains one of the most studied and iconic exoplanets because of its extreme weather and unique appearance. It is often used in media as the prototype of an alien world with terrifying conditions. Kepler, 438 billion reals. Kepler 438 billion reals is a rocky super-Earth orbiting a red dwarf star, about 470 light-years away. It was discovered in 2015 by the Kepler Space Telescope and was initially reported as one of the most Earth-like exoplanets known. The planet's radius is about 1.12 times that of Earth, making it slightly larger, and it receives roughly 1.4 times the amount of stellar radiation Earth does. Its orbital period is about 35 days, and its semi-major axis is only 0.166 astronomical units, placing it within what is technically the habitable zone of its star. However, the star Kepler 438 is highly active. It produces superflares that are 10 to 100 times more energetic than the strongest solar flares from the Sunday. These outbursts almost certainly stripped away the planet's atmosphere, if one ever existed. Without an atmosphere, Kepler 438 billion reals cannot retain liquid water, regulate surface temperature, or provide protection from stellar radiation. While its equilibrium temperature of about 276 Kelvin might seem Earth-like, the lack of an atmospheric greenhouse effect likely leaves the planet barren and hostile. Kepler 438b's mass is not well constrained but is believed to be less than twice Earth's mass, consistent with a rocky composition. The planet is likely tidally locked, meaning one hemisphere permanently faces its star, while the other remains in darkness. This would further destabilize climate without a protective atmosphere to distribute heat. This planet became well known in 2015 as a potential Earth twin and was even given the highest Earth similarity index at the time. But as further studies revealed the destructive stellar activity of its host, optimism about habitability faded. Today, Kepler 438 billion reals is used as a cautionary case study of how a planet can appear ideal by size and orbit, yet be rendered uninhabitable by its star's violent behavior. 55 Cancri e. This planet, also called Janssen, is a super-Earth orbiting the Sun-like star 55 Cancri A, located about 41 light-years away. It was discovered in 2004 by radial velocity measurements, and its transit was confirmed in 2011. The planet is extremely close to its star at just 0.016 astronomical units, completing one orbit in only 17.5 hours. Its mass is about 8 times that of Earth, and its radius is nearly twice Earth's, leading to a very high density of around 6 to 7 grams per cubic centimeter. This suggests a rocky or iron-rich composition with very strong surface gravity, about 4 times that of Earth. The planet is tidally locked, so one side faces perpetual day while the other side remains in darkness. The dayside temperature is extreme, between 2000 and 2800 Kelvin, which equals about 3600 to 5000 degrees Fahrenheit. This heat may melt surface rocks into vast lava lakes or even a global magma ocean. The night side, although cooler, is still around 1300 Kelvin. The atmosphere of 55 Cancri e remains uncertain. Early theories proposed a hydrogen, helium, or carbon dioxide atmosphere, but newer James Webb Space Telescope observations suggest it might contain water vapor mixed with carbon monoxide or carbon dioxide. Some earlier speculation proposed that because the star has a high carbon-to-oxygen ratio, the planet could be carbon-rich, leading to the nickname Diamond Planet. While this idea remains unproven, it became popular in media and public discussions. 55 Cancri e is also one of the most variable rocky exoplanets ever observed, showing changes in infrared brightness, which may indicate volcanic activity, heat transport, or atmospheric changes. Its extreme environment makes it an important target for understanding close-in super-Earths and their survival near stars. However, with its scorching temperatures and molten landscape, it is completely uninhabitable. WASP-12b. WASP-12b is a hot Jupiter located about 1400 light-years away, orbiting a Sun-like G-type star. It was discovered in 2008 by the Wide-Angle Search for Planets (WASP) survey using the transit method. The planet orbits extremely close to its star at only 0.0229 astronomical units, completing one orbit in just over one day. Its mass is about 1.4 times that of Jupiter, while its radius is about 1.8 times Jupiter's teams, giving it an unusually low density. The planet is tidally locked, so one hemisphere always faces its star. Its day side reaches temperatures above 3,100 Kelvin, or about 5,100 degrees Fahrenheit, while the night side is about 2,000 degrees Fahrenheit cooler. WASP-12b is tidally distorted into an egg-like shape due to the intense gravitational pull from its star. Its atmosphere is so extended that it overflows its Roche lobe, the region where a planet's gravity can hold onto material, and gas is actively being stripped away and pulled into the star. This makes WASP-12b one of the few planets observed to be cannibalized by its star. The atmosphere is rich in exotic chemistry. Early claims suggested it might have a carbon-to-oxygen ratio greater than 1, implying a carbon-dominated carbon planet. While this is debated, the planet's very dark appearance is well established. It reflects only about 6% of incoming light, making it one of the darkest exoplanets known. It absorbs 94% of starlight, converting most of it into heat. WASP-12b became one of the first exoplanets where scientists detected a secondary eclipse, revealing direct light from the planet itself. Studies using Hubble, Spitzer, and now the James Webb Space Telescope continue to refine our understanding of its composition and mass loss. Because of its unstable state, Washington SP-12b is expected to eventually disintegrate as it loses more material to its star. This makes it a unique laboratory for studying planetary death and star-planet interactions. Gliese 581c. Gliese 581c is a super-Earth orbiting the red dwarf star. Gliese 581, about 20 light-years away in the constellation Libra. It was discovered in 2007 using radial velocity measurements from the HARP spectrograph. At the time, it was hailed as one of the first potentially habitable exoplanets, but later studies revealed it is far too hot to sustain Earth-like life. The planet orbits at about 0.073 astronomical units from its star, completing a full orbit in nearly 13 days. Its minimum mass is estimated between 5 and 7 Earth masses, with a likely rocky composition. Its radius is estimated around 1.5 Earth radii. Due to its close orbit, it is almost certainly tidally locked, with one hemisphere always facing the star. Early models suggested that Gliese 581c might fall within the habitable zone, but greenhouse effects are believed to raise its surface temperature to between 700 and 1000 Kelvin, making it closer to Venus than Earth. Its atmosphere, if it exists, is likely dominated by carbon dioxide, creating a runaway greenhouse effect. This would leave the day side boiling hot, while the night side remains frozen. The discovery generated excitement as one of the first Earth-like exoplanets, but follow-up studies corrected this optimism. The planet is now considered a Venus analog, with extreme conditions unsuitable for liquid water or life. Its possible atmosphere remains unconfirmed, but if volcanic activity is present, it could maintain a thick, toxic blanket of gases. Gliese 581c remains important historically because it marked the beginning of the search for habitable super-Earths and highlighted the difficulty of defining habitability. While it is unlikely to host life, it serves as a warning that not all planets in the habitable zone truly offer habitable conditions. HD 106906b. HD 106906b is a massive gas giant orbiting a young binary star system, about 336 light-years away. It was discovered in 2013 through direct imaging, making it one of the rare exoplanets observed visually rather than through indirect methods like transits or radial velocity. The planet is estimated to have a mass of around 11 times that of Jupiter, placing it at the boundary between a giant planet and a brown dwarf. Its radius is about 1.5 times Jupiter's plaster. Because the system is only about 15 million years old, HD 106906b is still contracting and glowing from its internal heat, with an effective temperature around 1800 Kelvin. Its orbit is extraordinary. The planet lies about 738 astronomical units from its stars, over 700 times the Earth's Sunday distance, and about 100 times Neptune's distance from the Sunday. A single orbit likely takes 10,000 to 100,000 years. The orbit is also inclined by about 21 degrees relative to the system's debris disk, suggesting it was scattered outward by gravitational interactions or possibly captured from another star system. HD 106906b has no known moons or rings, but given its wide orbit and young age, it could in principle host a circumplanetary disk that might form moons in the future. Its unusual placement has drawn comparisons to the hypothesized Planet 9 in our own solar system. In 2022, the James Webb Space Telescope directly imaged HD 106906b, further confirming its status as a unique and extreme exoplanet. Its existence challenges traditional models of planet formation, since such a massive planet is unlikely to have formed so far away from its host stars. Scientists continue to debate whether it was ejected outward from a closer orbit or captured during an early stellar encounter. HD 106906b is not habitable, but its wide separation, brightness, and young age make it an important laboratory for studying how giant planets form, evolve, and sometimes end up on bizarre orbits. TRES 2b, Kepler 1 billion reals. TRES 2b, also known as Kepler 1 billion reals, is a hot Jupiter located about 750 light-years away, orbiting a Sun-like G0 volt star. It was discovered in 2006 by the Transatlantic Exoplanet Survey, TRES, and was later observed extensively by the Kepler Space Telescope. Its orbit lies extremely close to its star, at only 0.0356 astronomical units, completing a full orbit in just 2.47 days. The planet's mass is roughly 1.2 times that of Jupiter, with a radius of about 1.23 Jupiter radii. This gives it a density of about 1.16 grams per cubic centimeter, consistent with a gas giant structure composed primarily of hydrogen and helium. The equilibrium temperature of TRES 2b is estimated at about 1885 Kelvin, or more than 1600 degrees Celsius. It is almost certainly tidally locked, with one hemisphere permanently facing its star while the other is in perpetual night. This creates a strong temperature gradient, but the atmosphere likely redistributes some of the heat through high-speed winds. What makes TRES 2b extraordinary is its albedo, or reflectivity. It reflects less than 1% of incoming starlight, making it the darkest known exoplanet. For comparison, charcoal reflects about 4% of light, and fresh asphalt reflects about 5%. TRES 2b absorbs nearly all the light that strikes it, making it virtually invisible in visible wavelengths. It emits only a faint infrared glow due to its heat. The exact cause of this extreme darkness remains uncertain. One explanation is that its atmosphere contains chemicals such as vaporized titanium oxide, sodium, or potassium that strongly absorb visible light. Another possibility is the absence of reflective clouds, which other hot Jupiters often possess. Its darkness suggests a unique balance of atmospheric chemistry and temperature. Despite being invisible to human eyes, TRES 2b was observed by Kepler through its transit signal and the slight dip in brightness when it passed behind its star, known as a secondary eclipse. These observations provided direct measurements of its reflectivity. The planet became a landmark example, showing that not all hot Jupiters share the same reflective properties. TRES 2b is uninhabitable as a gas giant with extreme heat and no solid surface, but its existence highlights the diversity of planetary atmospheres and the surprising outcomes of chemistry under intense irradiation. It continues to serve as a key object for testing atmospheric models and for understanding how exoplanets process light from their stars. PSR B1620, MICE 26, B, Methuselah. PSR B1620, MICE 26b, nicknamed Methuselah, is one of the oldest known planets in the universe. With an estimated age of about 12.7 billion years, nearly 3 times the age of Earth, it orbits a remarkable system located in the globular cluster M4, about 12,000 light-years away, where its hosts are a binary pair, a millisecond pulsar, and a white dwarf star. The pulsar is a rapidly rotating neutron star left over from a supernova, while the white dwarf is the stellar core of a dead sun-like star. The planet itself is a gas giant with a mass of about 2.5 times Jupiter's. It orbits the pulsar white dwarf binary at a distance of about 23 astronomical units, which is similar to Uranus's distance from the Sunday. The orbital period is very long, nearly 100 years, with a moderate eccentricity of about 0.13, Methuselah's temperature is extremely cold, with equilibrium estimates around 60 Kelvin, or minus 350 degrees Fahrenheit, since it is far from its faint host stars. Its atmosphere is likely hydrogen and helium, and it produces no internal heat beyond what remains from its ancient formation. What makes this planet extraordinary is its survival story. To exist in its current orbit, it had to either survive the violent supernova explosion that created the pulsar, or it was captured later by the binary system. Both scenarios are difficult. A supernova typically destroys or ejects nearby planets, while capture requires rare dynamical interactions in the dense stellar environment of a globular cluster. Its very existence demonstrates that planets could form early in the universe, even in metal-poor environments, and could endure for billions of years through extreme astrophysical events. Methuselah was discovered in 1993 through pulsar timing measurements, which detect small variations in the pulses from the neutron star caused by the gravitational tug of an orbiting planet. In 1998, further refinements confirmed its planetary nature. It became the first exoplanet ever discovered in a globular cluster, and the first found orbiting a pulsar. The planet has cultural and scientific significance as a fossil world from the early universe. It proves that planets were already forming less than 2 billion years after the Big Bang, long before Earth existed. Although uninhabitable due to its cold environment and radiation from its pulsar host, Methuselah remains a vital piece of evidence in understanding the longevity and resilience of planetary systems across cosmic history. GJ 1214b. GJ 1214b is a super-Earth exoplanet located about 48 light-years away, orbiting a red dwarf star in the constellation Ophiuchus. It was discovered in 2009 by the MERTH project through the transit method, and it quickly became famous as one of the best-studied small exoplanets outside our solar system. Its mass is about 8.4 times that of Earth, with a radius of 2.7 Earth radii. This combination gives it a relatively low density of around 1.87 grams per cubic centimeter, much lower than Earth's 5.5. This suggests that GJ 1214b is not purely rocky, but must contain large amounts of lighter materials such as water, hydrogen, or other volatiles. It has been described as a possible water world or a mini-Neptune. The planet orbits very close to its star at a distance of only 0.014 astronomical units, completing a full orbit in just 1.58 days. Because of this proximity, it is tidally locked, with one side in perpetual daylight and the other in eternal night. Its equilibrium temperature is around 393 Kelvin, or about 120 degrees Celsius, but measurements of its atmosphere indicate that the day side reaches about 280 degrees Celsius, while the night side remains cooler at about 164 degrees Celsius. Its atmosphere is one of its most studied features. Early observations with the Hubble Space Telescope revealed a featureless transmission spectrum, which means that thick clouds or haze block light from deeper atmospheric layers. This prevented scientists from directly detecting specific molecules. For years, GJ 1214b was known as the flatline planet because its atmospheric signal showed no clear features. More recently, the James Webb Space Telescope made major advances. JWST observations revealed that the atmosphere is cloudy, but likely contains water vapor and possibly methane or carbon dioxide. This confirms that GJ 1214b has a volatile-rich envelope, possibly hundreds of kilometers thick, above a deep interior. Some models predict a global ocean that could be thousands of kilometers deep, compressed under immense pressure into exotic phases of hot ice or supercritical water. Because of its intermediate mass and radius, GJ 1214b represents a class of planets sub-Neptunes that have no counterpart in our solar system. It is critical for studying the boundary between rocky terrestrial planets and gas giants. Its atmosphere may contain key clues to how such worlds form and evolve. Though uninhabitable due to its extreme pressure, temperature, and lack of a solid surface, GJ 1214b is one of the most important exoplanets for atmospheric characterization. It continues to serve as a prototype for water-rich planets and demonstrates how cloud layers can conceal the true nature of alien atmospheres. Kepler 16 billion reals. Tatooine. Kepler's 16 billion reals is a gas giant orbiting 2 stars instead of 1, making it the first confirmed circumbinary planet. It lies about 200 light-years away and was discovered in 2011 by the Kepler Space Telescope. Its discovery demonstrated that stable planets can exist in binary star systems, a scenario long thought to be unlikely. The planet has a mass about 1/3 that of Jupiter, similar to Saturn, and a radius about 75% of Jupiter's 75%. It orbits the combined barycenter of its host, stars a K-type star and an M-type star, at a distance of about 0.7 astronomical units. Its orbital period is roughly 229 days, making its year similar in length to Earth's but far colder. With an estimated temperature of around 188 Kelvin, or -85 degrees Celsius, Kepler's 16 billion reals is a frigid gas giant with no solid surface. Its atmosphere is likely hydrogen and helium, resembling that of Jupiter or Saturn. As with other gas giants, any habitable potential would not come from the planet itself, but from possible moons, though none have yet been detected. One of the most remarkable aspects of Kepler's 16 billion reals is its orbital geometry. Because the planet transits both stars, astronomers could observe its motion with extraordinary precision. This allowed scientists to determine not only the planet's mass and radius, but also the orbits and masses of its 2 stars. Its nearly circular orbit and stability show that circumbinary planets can endure despite the gravitational complexity of dual suns. The cultural significance of Kepler's 16 billion reals is immense. It is often called the real Tatooine, referencing the fictional desert planet from Star Wars that orbits 2 suns. Images of double sunsets are strongly associated with this discovery, and it remains one of the most iconic exoplanets for public outreach. From a scientific perspective, Kepler's 16 billion reals proved that planet formation in binary star systems is possible and may be common. It opened an entirely new field of exoplanet research, inspiring astronomers to search for more circumbinary planets in Kepler data and beyond. While it is inhospitable due to its cold, gaseous nature, its existence provides key insights into planetary dynamics in complex stellar systems. Celt 9b. Celt 9b is the hottest exoplanet discovered so far, orbiting a blazing A-type star about 670 light-years away. It was found in 2017 by the Kilodegree Extremely Little Telescope (KELT) survey. Using the transit method, the planet is a massive gas giant, with a mass between 2.1 and 2.9 times that of Jupiter and a radius about 1.9 times larger. Its orbit is extremely close at only 0.0346 astronomical units, and it circles its host star in just 1.5 days. Because of this tight orbit, Celt 9b is tidally locked, with one side permanently facing its star and enduring unrelenting radiation. The dayside temperature reaches an astonishing 4,600 Kelvin, which is hotter than many small stars. At these temperatures, molecules cannot survive intact. Instead, hydrogen molecules split into atomic hydrogen, and metals such as iron, magnesium, and titanium exist in vaporized, ionized states. The atmosphere is essentially a plasma, resembling stellar conditions more than planetary ones. Observations show that the atmosphere is expanding and escaping into space, forming a comet-like tail of hydrogen and metals. The planet may be slowly evaporating under the extreme ultraviolet radiation of its host star. High-resolution spectroscopy has revealed the signatures of vaporized iron and titanium ions, while atomic hydrogen has been detected streaming away. The planet's night side is still extremely hot, but about 1,000 Kelvin cooler than the day side. The difference creates strong winds that redistribute heat, although not enough to balance the temperatures fully. Any potential moon or ring system would be unstable and destroyed by the radiation environment. Culturally, Celt 9b has been widely described as the hottest world known, with some media noting it is hotter than certain red dwarf stars. Its discovery expanded the definition of what planetary atmospheres can endure and challenged models of atmospheric chemistry, since conditions on this planet push beyond what was thought possible. From a scientific standpoint, Celt 9b is critical for understanding atmospheric escape and the survival of gas giants around massive stars. It demonstrates how close-in exoplanets can blur the boundary between planets and stars, offering a rare opportunity to study extreme irradiation effects. The James Webb Space Telescope and ground-based instruments continue to monitor it, seeking to determine its long-term fate. WASP 76b is an ultra-hot Jupiter orbiting an F-type star about 637 light-years away. It was discovered in 2013 by the Wide-Angle Search for Planets (WASP) project using the transit method. The planet is nearly twice the size of Jupiter, with a mass about 92% that of Jupiter. Its orbit is very tight at only 0.033 astronomical units, and it completes a full orbit in just 1.8 days. The dayside temperature is extreme, reaching about 2400 degrees Celsius or 4300 degrees Fahrenheit. At this temperature, iron and other metals vaporize into a gaseous state. On the cooler night side, these metals condense and fall as rain, creating what astronomers call iron rain. This makes WASP 76b one of the most dramatic examples of exotic planetary weather ever discovered. Its atmosphere is inflated and extended, with clouds of silicate particles and metals forming at different altitudes. Observations using high-resolution spectroscopy detected neutral iron in the atmosphere, confirming the presence of vaporized metals. The strong temperature contrast between the day and night sides drives powerful winds that may redistribute material around the planet. The planet's low albedo means it reflects very little light, absorbing most of the radiation it receives from its star. This contributes to its extremely hot conditions and unusual weather. Tidally locked, the same hemisphere always faces the star, where iron is continually vaporized, while the perpetual night side becomes a deposition zone for metallic rain. Culturally, Washington SP-76b has been widely reported in media as a hell planet, where it literally rains molten iron. It is often cited in lists of the most alien and hostile exoplanets known. From a scientific perspective, Washington SP-76b is highly valuable for studying atmospheric chemistry under extreme conditions. It demonstrates how familiar elements like iron can behave in exotic ways when subjected to intense stellar radiation. Future studies with the James Webb Space Telescope aim to map its atmosphere in greater detail, including the distribution of iron, vapor, and cloud species. The planet itself is uninhabitable, but it offers a striking example of how extreme planetary weather can reshape our understanding of exoplanet climates. WASP 121b. WASP 121b is an ultra-hot Jupiter orbiting an F-type star about 858 light-years away. It was discovered in 2015 using the transit method. The planet is highly inflated, with a radius about 1.75 times that of Jupiter but only slightly more massive, at about 1.16 Jupiter masses. Its orbit is extremely tight at 0.025 astronomical units, with a period of only 1.27 days. The dayside temperature reaches around 2,600 Kelvin, or about 2,327 degrees Celsius, while the night side is about 1,500 Kelvin cooler. At these extreme conditions, many molecules break apart on the day side and then recombine on the cooler night side, driving complex chemical cycles. One of the most important discoveries about WASP 121b is the detection of a stratosphere, a temperature inversion layer in its atmosphere. This means that instead of cooling with altitude, as in most planetary atmospheres, a layer of WASP 121b's atmosphere heats up. This was the first confirmed case of a stratosphere on an exoplanet. The inversion is likely caused by molecules such as vanadium oxide and titanium oxide that absorb stellar radiation high in the atmosphere. The atmosphere itself is filled with exotic chemistry. Observations with the Hubble Space Telescope and Spitzer have detected water vapor, vanadium oxide, and hints of hydrogen dissociation. The atmosphere is also extremely extended, appearing almost balloon-like due to the planet's inflated radius and low density. Tidal forces from the host star stretch the planet into an elongated shape, and some models predict that WASP 121b is close to Roche lobe overflow, meaning material from its atmosphere could eventually escape into space. Its night side may host clouds of iron or silicates, while the day side is a blazing environment where such materials remain vaporized. Although uninhabitable, Washington SP-121b has become a benchmark object for studying hot Jupiter atmospheres. It demonstrates the presence of thermal inversions, complex chemical processes, and extreme atmospheric circulation. Observations with the James Webb Space Telescope are expected to refine our understanding of its structure and chemistry, making it a reference case for giant exoplanets enduring extreme irradiation. K2 to 141b. K2 to 141b is an ultra-short period super-Earth orbiting a K-type star about 61 light-years away. It was discovered in 2018 in data from NASA's K2 mission. The planet is extremely close to its star, at only 0.0075 astronomical units, and it completes one orbit in just 6.7 hours, making its year shorter than a single Earth day. Its mass is about 5 Earth masses, and its radius about 1.5 Earth radii, giving it a very high density of roughly 8 to 9 grams per cubic centimeter. This density suggests an iron-rich composition, making it similar to Mercury but on a larger scale. The planet is tidally locked, with one hemisphere enduring constant starlight, while the other is locked in endless night. The dayside temperature is extreme, around 3,300 Kelvin, or about 3,000 degrees Celsius. At these temperatures, the rocky surface is molten, forming a global magma ocean. The intense heat vaporizes rock into a thin, silicate atmosphere. Supersonic winds then carry this vapor from the blazing dayside to the frigid nightside, where it condenses and falls back as rock rain. The nightside temperature is drastically lower, around 70 Kelvin, colder than liquid nitrogen. This creates one of the most extreme temperature contrasts of any known exoplanet. K2 to 141b's atmosphere is therefore not composed of gases like oxygen or nitrogen, but rather vaporized minerals such as sodium, silicon monoxide, and other silicates. This cycle rock, evaporating on one side, condensing on the other, and raining back down resembles the water cycle on Earth but with stone instead of water. Its orbit and density also suggest that K2 to 141b has undergone violent evolutionary processes. It may have once possessed volatile layers such as water or a hydrogen envelope, but its star's intense radiation likely stripped them away, leaving only a dense iron core and magma surface. Culturally, K2 to 141b has been described as a lava planet or hell world, often appearing in popular media as an example of how extreme close-in exoplanets can be. Scientifically, it serves as an important case study for understanding the survival and composition of rocky planets under the harshest stellar conditions. It represents the extreme end of rocky planet evolution, essentially an Earth-like body, reduced to a magma, ocean, and mineral atmosphere by its proximity to its star. Kepler 78 billion reals. Kepler 78 billion reals is an ultra-short period. Earth-sized exoplanet orbiting a Sun-like star about 470 light-years away. It was discovered in 2013 through data from the Kepler Space Telescope. What makes this planet extraordinary is not only its small size, similar to Earth, but also its extremely close orbit that challenges existing models of planetary formation. The planet has a radius of about 1.2 Earth radii and a mass of about 1.7 Earth masses, yielding a density of roughly 5.4 grams per cubic centimeter, almost identical to Earth's. This strongly suggests a rocky composition with an iron core and silicate mantle, making it one of the most Earth-like planets in terms of structure. However, its orbit is one of the shortest known. Kepler 78 billion reals circles its star at only 0.0089 astronomical units, completing a full orbit in just 8.5 hours. At this distance, the planet is nearly 20 times closer to its star than Mercury is to the Sunday tidal. Locking ensures one side is constantly roasted by its star, while the other side is locked in eternal darkness. The dayside temperature is estimated to reach between 2,000 and 3,000 Kelvin, hot enough to melt rock. The surface is likely covered by a global magma ocean. The night side, in contrast, may be extremely cold. This temperature difference could produce an exotic atmosphere composed of vaporized rock, with mineral vapors transported by fierce winds and condensing as rock rain on the cooler hemisphere, similar to processes modeled for other lava planets like K2 to 141b. The most puzzling aspect of Kepler 78 billion reals is its formation. Standard models suggest it is nearly impossible for a rocky planet of this size to form and remain stable so close to a star. Theories propose it may have migrated inward from a more distant orbit, or that it is the stripped core of a larger body whose outer layers were blown away. Its existence forces astronomers to reconsider how planetary systems evolve and how many extreme cases like this may exist. Kepler 78 billion Reals is uninhabitable due to its extreme heat and unstable conditions, but its Earth-like density and tiny orbit make it one of the most intriguing rocky exoplanets discovered. It stands as a key example of how planets similar in size to Earth can exist in completely alien environments, reshaping our understanding of terrestrial planet diversity. Kepler 22 billion Reals. Kepler 22 billion Reals is a super-Earth, or mini-Neptune, orbiting a Sun-like star about 620 light-years away in the constellation Cygnus. It was discovered in 2011 by NASA's Kepler Space Telescope and became the first confirmed exoplanet located in the habitable zone of its parent star. This generated worldwide interest, as it was initially considered a strong candidate for potential habitability. The planet has a radius about 2.4 times that of Earth. Its mass is uncertain but is estimated to be between 5 and 36 Earth masses, depending on its interior composition. Its size places it near the poorly understood radius gap, where planets transition between rocky, super-Earths and volatile, rich mini-Neptunes. This means it could either be a rocky, super-Earth with oceans or a gaseous world with a thick hydrogen-helium envelope. Kepler 22 billion Reals orbits its G-type star at a distance of about 0.85 astronomical units, which is close to Earth's orbital distance from the Sun. Its orbital period is about 290 days, again similar to Earth's. The star is slightly cooler and smaller than the Sun, but because the planet orbits within the habitable zone, its equilibrium temperature is estimated at around 260 Kelvin or minus 13 degrees Celsius. With an atmosphere containing greenhouse gases, surface temperatures could be much warmer, potentially allowing for liquid water. The planet is very likely tidally locked, which would result in one hemisphere facing the star permanently while the other remains in darkness. Climate models suggest that if it possesses a dense atmosphere or oceans, heat could be redistributed, possibly making parts of the planet habitable. However, without direct atmospheric measurements, its true nature remains uncertain. Culturally, Kepler 22 billion Reals was widely reported in 2011 and was often described as a possible Earth 2.0. It inspired significant public imagination and continues to be featured in discussions about habitable zone exoplanets. Scientifically, it highlighted the limitations of early Kepler discoveries, showing that while orbital data can place a planet in the habitable zone, actual habitability depends on atmosphere, composition, and stellar activity. Future telescopes, especially the James Webb Space Telescope and large ground-based observatories, may be able to study its atmosphere through transit spectroscopy, although its relatively large distance makes this challenging. Whether Kepler 22 billion Reals is a super-Earth with oceans or a mini-Neptune with a thick gas envelope remains one of the key unanswered questions. Kepler 452 billion Reals. Kepler 452 billion Reals is often called Earth's cousin because it was the first discovered Earth-sized planet in the habitable zone of a Sun-like star. It orbits a G2-type star, very similar to our Sun, about 1,400 light-years away in the constellation Cygnus. The discovery was announced in 2015 using data from NASA's Kepler Space Telescope. The planet has a radius about 1.6 times that of Earth. Its mass is not precisely known, but is estimated to be up to 5 Earth masses, giving it a gravity roughly twice Earth. This size places it on the boundary between a rocky super-Earth and a volatile-rich mini-Neptune. If it is rocky, it may have a thick atmosphere and potentially surface oceans, although no atmosphere has been confirmed. Kepler 452 billion Reals orbits its star at a distance of 1 astronomical unit, the same as Earth's distance from the Sun, with a year lasting 385 days. Its star is slightly older, hotter, and brighter than our Sun, which means the planet receives about 10% more stellar radiation than Earth. The equilibrium temperature suggests that if it has an Earth-like atmosphere, surface conditions might be warm enough for liquid water, but potentially trending toward a runaway greenhouse effect over geological timescales. Because the host star is about 1.5 billion years older than the Sun, Kepler 452 billion Reals may be experiencing an advanced stage of climate evolution. If it is rocky and has oceans, they may already be evaporating as the star brightens with age. This would gradually drive the planet toward Venus-like conditions, where water loss and greenhouse heating transform it into a hot, uninhabitable world. The cultural impact of Kepler 452 billion reals was significant. NASA's announcement in 2015 generated headlines worldwide, with many outlets describing it as the most Earth-like exoplanet yet. It was hailed as a milestone in the search for another Earth, even though its true habitability remains uncertain. Scientifically, Kepler 452 billion reals underscores the importance of stellar age in evaluating habitability. Even if a planet is Earth-sized and in the habitable zone, its star's long-term evolution may eventually strip it of water and render it barren. This case illustrates how habitability is not static but evolves over billions of years as stars change. Future missions capable of atmospheric characterization, such as JWST or next-generation ground telescopes, will be required to determine whether Kepler 452 billion reals has any gases indicating oceans or biological potential. Kepler 62 Farad. Kepler 62 Farad is a super-Earth orbiting a K-type star about 1,200 light-years away in the constellation Lyra. It was discovered in 2013 by NASA's Kepler Space Telescope and is one of 5 known planets in the Kepler 62 reals system. Of those, Kepler 62 Farad stands out because it lies within the star's habitable zone. The planet has a radius about 1.4 times that of Earth. Its mass has not been measured directly, but is estimated to be between 2 and 3 Earth masses if it is rocky. This size suggests a strong likelihood of a solid surface with higher gravity than Earth's. Kepler 62 Farad orbits its star at about 0.71 astronomical units, completing one orbit every 267 days. The host star is smaller and cooler than the Sun, so the planet receives less stellar energy than Earth, placing it near the outer edge of the habitable zone. Its equilibrium temperature is around 200 Kelvin, much colder than Earth's, which means that without a thick atmosphere, its surface would be frozen. Climate models suggest that if Kepler 62 Farad has an atmosphere rich in carbon dioxide or other greenhouse gases, it could trap enough heat to sustain liquid water. In particular, a dense carbon dioxide atmosphere, comparable to early Mars or Earth, could create stable conditions for oceans. Tidal locking is possible due to its orbit, which could further complicate climate, but models show that even tidally locked planets could maintain habitable zones along the terminator, the boundary between day and night if the atmosphere is thick enough to circulate heat. The system also contains another habitable zone planet, Kepler 62 reals e, which is slightly larger and closer to the star, making Kepler 62 reals one of the first multi-planet systems with potentially habitable worlds. This has made it a focus for research into how multiple habitable zone planets interact and evolve. Culturally, Kepler 62 Farad is often listed among the most promising Earth-like exoplanets. It has been highlighted in scientific studies and media discussions of exo-Earth candidates, although no atmosphere or surface conditions are confirmed. From a scientific standpoint, Kepler 62 Farad demonstrates the importance of atmosphere in defining habitability. While it is Earth-sized and in the habitable zone, whether it is a frozen wasteland or an ocean-covered world depends entirely on its atmospheric properties, which remain unknown. Future telescopes may attempt to study its atmosphere through transit spectroscopy if conditions allow. Kepler 186 Farad. Kepler 186 Farad is one of the most celebrated exoplanets because it was the first Earth-sized planet discovered within the habitable zone of its star. It orbits a red dwarf about 580 light-years away in the constellation Cygnus. The discovery was announced in 2014 using data from NASA's Kepler Space Telescope. The planet has a radius about 1.1 Earth radii, making it almost the same size as Earth. Its mass has not been directly measured, but models suggest it is likely less than 2 Earth masses, consistent with a rocky composition. This makes it one of the closest analogs to Earth in terms of physical size. Kepler 186 Farad orbits at about 0.35 astronomical units, with an orbital period of 130 days. The host star is a cooler M dwarf, so despite its closer orbit, the planet receives only about 1/3 of the energy Earth gets from the Sunday. This places it near the outer edge of the habitable zone. Its equilibrium temperature is estimated around 188 Kelvin, colder than Earth, meaning it would require a substantial greenhouse effect to maintain liquid water on its surface. Because of its proximity to a red dwarf, Kepler 186 Farad is likely tidally locked. One hemisphere would remain in constant daylight, while the other is in permanent night. This raises questions about climate stability. But models suggest that with a thick enough atmosphere, heat could circulate and create temperate zones, particularly along the terminator line between day and night. The host star's activity is another critical factor. Red dwarfs are known for frequent flares and bursts of radiation, which can strip planetary atmospheres. The survival of Kepler 186 Farad's atmosphere is uncertain. If it has managed to retain one, it could still be habitable. Without it, the planet would be barren and frozen. Culturally, Kepler 186 Farad attracted enormous attention as Earth's cousin, or a potential second Earth. NASA described it as a step closer to finding a world similar to Earth. It remains a symbol in the search for habitable exoplanets, and has been widely featured in media and scientific literature. Scientifically, Kepler 186 Farad highlights the challenges of assessing true habitability. While size and orbital location suggest potential, the atmosphere and stellar activity ultimately determine its fate. Future missions, such as JWST and extremely large ground-based telescopes, may eventually probe for atmospheric signatures. Until then, Kepler 186 Farad remains one of the best candidates for a potentially Earth-like world, though its true nature is still unknown. Proxima Centauri b. Proxima Centauri b is the closest known exoplanet to Earth. Orbiting Proxima Centauri, the nearest star to the Sun at only 4.2 light-years away, it was discovered in 2016 by the European Southern Observatory using the radial velocity method. This proximity makes it one of the most important and intensively studied exoplanets. The planet has a minimum mass of about 1.1 Earth masses, strongly suggesting it is rocky. Its radius has not been measured directly, but is assumed to be close to Earth's Bresis. It orbits within the star's habitable zone at a distance of about 0.05 astronomical units, completing one orbit in only 11.2 days. Proxima Centauri is a red dwarf star, much cooler and dimmer than the Sun, but it is also highly active. It frequently produces powerful stellar flares and bursts of ultraviolet and X-ray radiation. These flares may strip away a planet's atmosphere over time, raising questions about the long-term habitability of Proxima Centauri b. The equilibrium temperature of the planet is estimated to be about -39 degrees Celsius, but with a suitable atmosphere, greenhouse warming could raise surface conditions enough for liquid water. If the planet is tidally locked, as is likely, one hemisphere would be in constant daylight and the other in permanent darkness. Atmospheric circulation or oceans could help redistribute heat, but without an atmosphere, the climate would be extremely harsh. Proxima Centauri b quickly became a cultural phenomenon after its discovery because it is the closest potentially habitable world to Earth. It has been the subject of countless news stories, scientific papers, and even interstellar mission proposals, such as Breakthrough Starshot, which envisions sending tiny laser-powered spacecraft to the system within a human lifetime. Scientifically, Proxima Centauri b represents both promise and uncertainty. Its Earth-like mass and location in the habitable zone make it a prime target in the search for life. Yet the violent stellar activity of its host star may render it sterile. Ongoing and future observations with instruments like JWST, the Extremely Large Telescope, and next-generation radial velocity surveys aim to detect its atmosphere, if one exists, and assess its potential for habitability. Tau Ceti e. Tau Ceti e is a super-Earth orbiting the nearby Sun-like star Tau Ceti, located just 12 light-years away in the constellation Cetus. It was discovered in 2012 using the radial velocity method and quickly attracted attention because of its proximity and its placement near the inner edge of the star's habitable zone. The planet has a minimum mass of about 4.3 Earth masses. Its radius has not been directly measured, but is likely around 1.6 Earth radii if it is rocky. This makes Tau Ceti e significantly larger than Earth, with stronger surface gravity. Tau Ceti e orbits its star at about 0.61 astronomical units, completing one orbit in 163 days. Since Tau Ceti is slightly smaller and cooler than the Sun, This orbit places Tau Ceti e just inside the habitable zone. However, because of its position, it likely receives nearly twice the stellar radiation that Earth does. This raises the possibility that Tau Ceti could be more like a super-Venus, with high temperatures and potentially a runaway greenhouse atmosphere. The habitability of Tau Ceti e depends heavily on its atmosphere. If it has a thick carbon dioxide atmosphere, its surface would likely be far too hot for liquid water. On the other hand, if its atmosphere is thin or reflective clouds help moderate heating, parts of the surface could be temperate. No atmosphere has yet been detected. Tau Ceti is notable for being a relatively quiet star, with less flare activity than many red dwarfs. This makes it more favorable for long-term atmospheric retention. The star also has a massive debris disk, somewhat like our Kuiper belt, which could increase the chances of cometary bombardments and impact hazards for planets in the system. Culturally, Tau Ceti e gained attention because Tau Ceti has long been a popular star in science fiction, often portrayed as hosting habitable planets. The discovery of real super-Earths in this system gave new weight to those depictions. From a scientific standpoint, Tau Ceti e is important because of its similarity to Earth in terms of host star type and its relative closeness to our solar system. Future missions could target it for direct imaging or atmospheric spectroscopy. While it is unlikely to be habitable due to high stellar flux, it remains one of the most intriguing nearby super-Earths. LHS 1000, 140b. LHS 1000, 140b is a rocky super-Earth orbiting a red dwarf star about 40 light-years away in the constellation Cetus. It was discovered in 2017 using the transit method with the M-Earth project and confirmed by radial velocity measurements. Because of its size, density, and position within its star's habitable zone, it is considered one of the most promising exoplanets for atmospheric characterization. The planet has a radius about 1.4 Earth radii and a mass about 6.6 Earth masses. This gives it a density of roughly 7.5 grams per cubic centimeter, significantly denser than Earth, suggesting a very large iron core. Its strong gravity would help it retain an atmosphere, even under the active radiation environment of a red dwarf star. LHS 1140b orbits at a distance of about 0.092 astronomical units, completing one orbit in 25 days. Despite its close orbit, its host star is small and dim, so the planet receives less stellar radiation than Earth does. Its equilibrium temperature is estimated at about 230 Kelvin, which is cold but could support liquid water with the aid of greenhouse warming. The host star is unusually quiet for a red dwarf, showing far fewer flares than stars like Proxima Centauri. This greatly increases the chances that LHS 1140b has retained an atmosphere over billions of years. If so, it could provide stable surface conditions, possibly including oceans. Observations with the Hubble Space Telescope have already searched for atmospheric signals, though detailed composition remains unclear. Future missions, particularly the James Webb Space Telescope, are expected to provide deeper insights into whether the planet has water vapor, carbon dioxide, or other greenhouse gases. Culturally, LHS 1140b has been described as one of the best places to look for life beyond Earth. Its combination of size, density, and habitable zone orbit makes it one of the top-ranked exoplanets on habitability indices. From a scientific perspective, LHS 1140b is invaluable because it bridges the gap between Earth-like rocky planets and larger super-Earths. Its strong gravity and potential atmosphere make it a key laboratory for studying habitability around red dwarfs. While no evidence of life has been detected, its relative closeness and favorable conditions mean it will remain a prime target for the search for biosignatures in the coming decades. TRAPPIST-1e. TRAPPIST-1e is one of 7 Earth-sized planets orbiting the ultra-cool red dwarf star TRAPPIST-1. Located about 40 light-years away in the constellation Aquarius. The system was discovered between 2016 and 2017 using WASP 121b. WASP 121b is a gas giant shaped like a stretched football due to the immense gravity of its parent star. Its dayside reaches about 3,000 degrees Celsius, hot enough to vaporize metals such as iron, magnesium, and chromium into gases. Water molecules here cannot survive intact. They split apart into hydrogen and oxygen under the extreme heat. On the cooler night side, the temperature is still around 1,500 degrees Celsius. Winds moving faster than 5 kilometers per second carry material from the day side to the night side, where hydrogen and oxygen recombine to form water vapor. In this violent cycle, metals condense and fall as rain made of liquid gems and metallic droplets. Standing here would mean being burned, blown across the planet at supersonic speed, and finally struck by gemstone rain at deadly velocity. GJ 1132b. GJ 1132b lies 41 light-years away and was once a Neptune-like gas planet. Radiation from its star stripped away the original atmosphere, leaving only a bare rocky core. Volcanic activity on the surface has since released new gases, forming a toxic secondary atmosphere. This atmosphere contains hydrogen, methane, smog-like hydrocarbons, and hydrogen cyanide. Hydrogen cyanide is especially lethal, used even in chemical warfare on Earth. Inhaling it causes dizziness, nausea, seizures, and death in very small doses. The heat from the planet's star keeps the surface scorched, while constant volcanic eruptions replenish the poisonous air. Anyone stepping onto this world without protection would die within moments, their lungs overwhelmed by deadly gases while surrounded by a hostile volcanic wasteland. Poltergeist planet. The Poltergeist planet orbits a pulsar, the dense remnant of a star that exploded as a supernova. A pulsar is a rapidly spinning neutron star with an intense magnetic field, blasting constant streams of radiation across space. Standing on this planet would mean being struck by gamma rays, X-rays, and charged particles with every rotation of the pulsar, like being caught in a strobe light of deadly energy. Radiation this powerful would destroy biological tissue instantly, and even strip atoms apart. In addition, the pulsar wind would continuously blast the planet with high-speed particles, eroding its surface and atmosphere. This is one of the most hostile environments possible in the universe. GJ 504b. GJ 504b is a gas giant, about 4 times larger than Jupiter. Its striking pink color comes from the heat left over from its formation. Since the planet is still relatively young at only 160 million years old. Despite its pleasant appearance, conditions here are fatal. The surface temperature is about 230 degrees Celsius, hot enough to scorch flesh. The gravity is 10 times stronger than Earth's, which would crush a human's body, making it nearly impossible for blood to circulate. Bones would snap under the pressure, and even walking would be impossible. Instead of a soft pink paradise, this is a deadly trap of heat and crushing gravity. LTT 9779b. LTT 9779b is the most reflective exoplanet ever found, with metallic clouds covering its atmosphere. These clouds reflect about 80% of the light from its star, making the planet dazzlingly bright. But its beauty hides lethal conditions. The daytime temperature reaches about 2,000 degrees Celsius, hot enough to vaporize metals into gas. These metallic vapors condense into clouds of titanium and silicate particles, filling the air with toxic materials. Breathing here would mean inhaling vaporized metals, burning the lungs from the inside. The intense brightness itself could even blind the human eye. This world is both blinding and poisonous, offering no chance of survival. L98 to 59d. L98 to 59d is 1.5 times the size of Earth and is the smallest known exoplanet with a detected atmosphere. At first glance, it might seem like a promising place to look for life, but its conditions are utterly hostile. The atmosphere is thick, with sulfur dioxide and hydrogen sulfide, gases that smell strongly of rotten eggs. These toxic compounds are released by volcanic activity across the planet's surface, triggered by the gravitational pull of its star. The constant eruptions keep the atmosphere filled with poisonous fumes. The surface itself is covered in magma oceans, with temperatures far above what any life could withstand. A human visitor would suffocate within seconds, with lungs burning from the acidic gases before being consumed by volcanic heat. Porphyrion. Porphyrion is not a planet, but a cosmic environment dominated by twin black hole jets. These jets extend 23 million light-years into space, powered by the immense gravitational energy of a supermassive black hole. The gas and dust falling into the black hole are superheated, and instead of disappearing, much of the material is blasted out at nearly the speed of light. Each jet releases energy equivalent to 1 trillion suns. Entering this region would mean being vaporized instantly by radiation and high-energy particles. No spacecraft could withstand the force. Even from a distance, the radiation is enough to sterilize entire star systems. 55. Cancri E. 55 Cancri E is a rocky planet about 41 light-years away. It orbits its star in only 18 hours, keeping one side locked permanently in daylight. The surface of the planet is covered in an ocean of molten lava, with temperatures hot enough to vaporize rock. Deep within, scientists believe the planet's carbon-rich interior may form diamond, earning it the nickname the Diamond Planet. Above, the skies sparkle with reflective silicate clouds, mirroring the glowing lava below. But despite its beauty, standing here means certain death. A human would be incinerated instantly in the lava ocean, with no chance of survival in its fiery, diamond-lit hellscape. TOI 849b. TOI 849b is the largest rocky planet ever discovered. It has no atmosphere, which means there is no protection from radiation or heat. Its orbit is extremely close to its star, giving it surface temperatures of about 1,500 degrees Celsius, or 2,700 degrees Fahrenheit. At those conditions, metal would melt instantly, and human tissue would burn away in seconds. With zero atmospheric pressure, even your blood would boil. No spacecraft could land safely here because the heat would destroy any shielding. Scientists believe this planet is the exposed core of a gas giant, stripped bare by its star's gravity. TRES 2b. TRES 2b is what astronomers call a hot Jupiter. It is a gas giant orbiting close to its star, about 750 light-years away. What makes it terrifying is its near-total darkness. This planet absorbs 99.9% of the light that touches it, more than any other known object in space. For comparison, coal on Earth absorbs 95% of light. On TRES 2b, you would see almost nothing but endless black. The only visible glow comes from the faint red radiation of its overheated atmosphere. Despite the darkness, the planet is still extremely hot due to its tight orbit. Anyone who arrived here would face both blinding darkness and lethal heat. Kepler 70b. Kepler 70b, once called KOI 55.01, is a planet that survived being swallowed by its star. It used to be as large as Jupiter, but when the star expanded into a red giant, the planet was engulfed by its outer layers. Friction stripped away its atmosphere and much of its bulk. What remains is now smaller than Earth, and burns at about 6,800 degrees Celsius or 12,000 degrees Fahrenheit. This is hotter than the surface of most stars. The planet is slowly evaporating and will eventually vanish entirely. Standing here would mean being burned to ash instantly, with even metals melting around you. Gliese 1214b. Gliese 1214b is known as a water world, about 8 times the mass of Earth. Unlike Earth, where water makes up only a thin outer layer, 3/4 of this planet's mass is water. The oceans are thousands of kilometers deep, far deeper than any trench on Earth. The upper layers are hot and steamy due to the planet's thick atmosphere. But as you descend, the pressure rises to crushing levels. At extreme depths, water does not remain liquid, but is forced into strange states, like plasma or exotic ices that cannot exist on Earth. A human here would be crushed instantly, while even robotic probes would fail under the extreme temperature and pressure. Celt 9b. Celt 9b is the hottest exoplanet ever discovered. This gas giant has a mass 3 times that of Jupiter, and it orbits so close to its parent star that a year lasts only 1.5 Earth days. Daytime temperatures exceed 4,300 degrees Celsius, or nearly 8,000 degrees Fahrenheit. At that heat, molecules themselves are ripped apart into individual atoms, so even if you were shielded, your body's chemistry would disintegrate. The radiation from its star is so strong that Celt 9b is constantly losing its atmosphere, slowly being stripped away into space. Over millions of years, it may completely erode away, leaving only a scorched core. WASP-12b. WASP-12b is a gas giant with 1.8 times the radius of Jupiter. Its orbit is so tight that it completes a year in just over a single Earth day. The gravity from its parent star pulls on it so strongly that the planet is stretched into an egg shape. This gravitational pull is also stripping material off its outer layers, pulling the planet apart piece by piece. In about 10 million years, WASP-12b will be entirely consumed by its star. Any visitor would face lethal tidal forces, where the difference in gravity between their head and feet would stretch their body apart. This world is not just hostile, it is actively being destroyed. AU Mike B. AU Mike B orbits a young red dwarf star that is only about 22 million years old. The star is unstable and releases frequent bursts of radiation, including powerful X-rays. These constant flares strip away the planet's hydrogen atmosphere, making it impossible for life to exist. The planet itself is also surrounded by a thick disk of dust that traps it in a hostile environment. Any spacecraft trying to land would be battered by high-energy particles and radiation, while the dust disk would make escape nearly impossible. Standing here would mean being bombarded by invisible radiation strong enough to destroy DNA within seconds. HD 80606b. HD 80606b has one of the strangest orbits of any known exoplanet. Instead of a nearly circular path, its orbit is stretched out like a comet. Every 111 days, it swings close to its parent star before moving far away again. During this close pass, the planet's temperature jumps from about 500 degrees Celsius to more than 1200 degrees Celsius in only 6 hours. This is like experiencing a massive explosion across the entire planet. The sudden heating drives violent winds that reach speeds of 17,000 kilometers per hour, or 11,000 miles per hour. Even if you survived the temperature spike, you would be torn apart by storms faster than any hurricane on Earth. K2